Well, a very good morning to you from Mission Control Houston. The reason we're here, right there on your screen. SpaceX's Dragon getting ready to depart from the International Space Station. It sits poised at the end of the Canadarm2 robotic arm, packed with over 4,100 pounds of science experiments, hardware, and other cargo from on board the International Space Station, just a few hours from splashing down in the Pacific Ocean after a very successful mission for one of NASA's two commercial cargo providers. Good morning, I'm NASA's Dan Hewitt, and we are joined here in the Mission Control Center in the Johnson Space Center in Houston, Texas, and we'll be bringing you live coverage as we get ready to say farewell to Dragon, the 11th Dragon, to visit the International Space Station. Here inside the room, the teams overseeing all the various systems on board the orbiting laboratory. They are led by Flight Director Dina Cantella, and she'll be leading the teams throughout all of the operations today. Again, Dragon already poised on the end of the robotic arm. It was detached from the Harmony module just earlier on Sunday. It is now officially Saturday or Monday, so I will try to keep the dates in order here, as it is 1 a.m. Central Time here in Houston. But Dragon detached from the Harmony module in the mid-afternoon, around 1:30 p.m. local time here in Houston. The Dragon had been attached there for several weeks since a successful launch from Florida and a flight up to the International Space Station, but it was detached and moved into its release attitude by flight controllers down here on the ground. The hatch had actually been closed back on Saturday afternoon, so a little more than 24 hours later, Dragon was detached and moved into where it sits now. You can see it with the Earth passing by in the background. The station and Dragon obviously just passed over the northern border of Spain, about to swing out over France and through Central Europe as it orbits the Earth at about 253 statute miles, traveling at over 17,500 miles an hour. The sun just came up on the Expedition 50 crew, who just woke up a short time ago with the release of Dragon, their first task, obviously, for the day. And on board right now, again, Expedition 52 crew, they're led by Russian cosmonaut Fyodor Yurchikhin, and then two NASA astronauts also on board, Jack Fisher and Peggy Whitson. The pair are going to be in the space station's cupola module, the bay window giving them a 360-degree view of the Earth below and of visiting spacecraft like Dragon. And they'll be at the robotic workstation, Jack Fisher Prime, so his hand will be on the trigger, and he'll be the one sending the release command to the robotic arm that will ultimately send Dragon on its way. That release is scheduled to come at 1:41 a.m. Central Time today, so we do have some time to get some more views of Dragon and just enjoy it a little while longer before it says farewell and makes its way back down towards Earth. Again, Dragon capable of re-entry, the only cargo ship capable of returning cargo right now in the fleet of vehicles going to and from the International Space Station. And that's why it's packed again with over 4,100 pounds of supplies today. Of that, a little over 1,400 pounds of utilization, so science hardware, so samples and other pieces of equipment from different research experiments conducted on board the International Space Station, and these research experiments coming from all space agencies around the globe, not just NASA, but our international partners, the Japan Aerospace Exploration Agency, the European Space Agency, and the Canadian Space Agency. And then in the NASA contingent, a lot of NASA experiments, but also a lot of experiments flown on board the International Space Station through the U.S. National Laboratory, these coming from academia and commercial sectors, as well as other government agencies, to take advantage of the microgravity laboratory, the only place you can really do this kind of research with taking gravity out of the equation, learning all sorts of new things about different processes, and we'll go into some of the research returning in just a little bit. But also in that 4,100 pounds, a lot of vehicle hardware, so just various pieces of space station hardware ready to come home, either for repair or analysis. A little under 1,400 pounds, 1,388 pounds to be exact. Also some spacewalking hardware, some crew supplies, and some computer resources on board as well. And just about 6 hours almost exactly after Dragon is released today. It'll be splashing down in the Pacific Ocean, just about 260 miles southwest of California, where teams from SpaceX will be standing by to pluck Dragon out of the water, put it on a boat, and tow it back into harbor. It'll get back, and then they'll immediately begin unloading some of the hardware. Some of those experiment samples have a finite clock on them to get them back to labs here back on planet Earth to resume the analysis. The experiments again taking place on board the station, returning and within 48 hours back in the hands of researchers back down here on the ground as for the science to continue. And again, that release time today, 1:41 a.m. Central, 2:41 a.m. Eastern Time. Should have plenty of sunlight over the next 40 minutes or so, so should have some good views of Dragon as it departs. Following its release, it'll drift for a few moments, and then it'll execute a series of 3 different burns, so firings of engines on the Dragon vehicle, and that'll move it away from the International Space Station, eventually getting out of what's known as the keep-out sphere and then the approach ellipsoid. These are imaginary areas around the station, defined distances where interaction between the teams here in Houston and the teams at SpaceX out at Hawthorne, California are coordinating, and those distances are in place for any vehicle visiting the International Space Station. Once it's out of the approach ellipsoid, the teams no longer interacting on a second-by-second basis, if you will, and then the team in Hawthorne fully in control and sending Dragon on its way again for that splashdown about 6 hours later. That splashdown at 7:41 a.m. Central Time, 8:41 a.m. Eastern. That'll be 5:41 a.m. in the morning over on the West Coast. For now, though, the teams here going through all their final checkouts. They'll do a final go, no-go with Dina Kotelik polling the team, and then they'll pass on that final go or no-go to the crew on board. Again, NASA's Jack Fisher and Peggy Whitson are going to be in the cupola. Jack Fisher, his hands on the controls. He'll be the prime today to send the command to send Dragon on its way. So again, this is the end of Dragon's successful mission. It launched back in early June on Saturday, June 3rd at 4:07 p.m. Central Time, launching, of course, on SpaceX's Falcon 9 rocket from Launch Complex 39A at NASA's Kennedy Space Center in Florida. The several-minute ride into orbit on top of the Falcon 9 delivered Dragon into its preliminary orbit, and then it had about a 2-day flight to the International Space Station, and it carried over 6,000 pounds of supplies to the orbiting laboratory, and that included a lot of research and vehicle hardware inside the pressurized, which you can see just at the very top of the rocket there, which is currently attached to the robotic arm right now, but also several thousand pounds of unpressurized cargo, which we can also go into in just a little bit. But again, that launch happening back in June, 2-day flight to the station. It was captured successfully on June 5th, and then it had been attached ever since. And then the release day will wrap up about a 1-month stay, again with a little over 4,100 pounds of cargo on board.
6:40 GMT, close at 07:05 GMT. And just for your essay, sunset is at 0650, but that has no impact to your release window.
Okay, copy. Our window is 0640 to 0705, and we're go for step 1 of 1.320, Dragon release.
You got it right, Peggy.
Expedition 52 flight engineer Peggy Whitson getting some words from the Capcom here in Houston. So just to explain that a little bit, their release window, that's when essentially the conditions are right that the crew could give the command to release Dragon. That'll open up at 1:40 a.m. Central Time. Once that release window is open, they can essentially execute that release at any time. Once the command is sent, it does take a little bit of time for Dragon to actually separate, as a series of hooks and snares inside of the robotic arm have to retract to basically let go of Dragon. The release expected to come at about 1:41 a.m. Central Time, so just 30 minutes from right now. And then Dragon will float away and then execute that series of burns. Now that release window will close at 2:05 a.m. Central Time. And so what that means is if Dragon hasn't been released by that point, they'll stand down, and then they have a backup release window where basically they'll wait about one orbit of the Earth, so they'll wait about 90 minutes, a little less in this case, and then the conditions will once again be right for the release, and then they'll be able to give it another go. That just to protect for any off-nominal, as we like to call it, but any out-of-the-ordinary situations, any issues with either the spacecraft or the robotic arm itself, everything, always having a backup plan. But the primary release window opening up in just a little while at 1:40 a.m. Central Time, 2:40 a.m. Eastern Time. And again, that release expected to come at just about 1:41 a.m. And again, Dragon returning a lot of science experiments today, but it also delivered a lot. And some of those are staying on board the International Space Station. Some that I'd just like to highlight real quick are some of the ones that rode up in the unpressurized section of Dragon, as we like to call it, the trunk. But these are extracted and installed on the outside of the International Space Station. And then they remain there either for the duration of the experiments or for the duration of their lifetime on orbit, as is the case with two of them. Over 2,000 pounds in weight of that initial launch load of over 6,000 pounds. One of those, which was installed, again, all of these operations were done by robotics controllers right here in Houston, and also up in Canada. The teams working in tandem to control the station's robotic arm, the Canadarm2. One of those that was installed was the NICER, the Neutron Star Interior Composition Explorer. And what that's going to be doing is taking a look at neutron stars. Now, neutron stars are some of the most unique bodies in our universe, some of the strangest things out there, and some of the most extreme stars as well. They're extremely dense remnants of very massive stars that have exploded and then collapsed into these spheres that are actually very small, especially if you're familiar with some of the celestial bodies out in the universe. A neutron star typically about the size of New York City, so very small when you think about things, on planetary and stellar scales. But while they're only about the size of New York City, they'll have more mass than our own sun, which basically gets you into a density to where if you just had 1 teaspoonful of neutron star matter and you had it here on Earth, in Earth's gravity, it would weigh about 1 billion tons. So again, very extreme, very unique stars out there. NICER is actually going to be taking a look at what makes them tick. And one of the really interesting things it's going to be looking at, though, is a form of a neutron star called a pulsar, which These are neutron stars that are spinning in very fast revolutions and then blasting out extreme amounts of X-rays. And so for an observer on Earth or anywhere else in the galaxy, these stars actually appear to pulse. And what NICER is going to be doing is it's going to be testing using these pulsars as a form of intergalactic GPS to see if it could use these pulsars to navigate throughout deep space. And this is something that not necessarily something that we would use when navigating our own stellar neighborhood, but when you start looking at going far beyond our own planet or even our own solar system, that is something that could conceivably use. So a little bit of space age technology, but something that we're developing and testing right now on board the International Space Station. One of the other payloads that was just flown up that's going to be there for the long haul is the MUSES. That's a multiple user system for Earth sensing facility. And you'll very quickly see why we use a lot of acronyms here at NASA with a lot of these long names for these payloads. But MUSES is actually going to be a platform for a number of different Earth imaging and Earth sensing devices that can actually be interchanged and changed out by the space station's robotic arm. The station providing a very unique vantage point, passing over the majority of the populated areas on planet Earth, and so hosting a lot of different instruments aimed right back down 250 miles below at the Earth to provide data on climate change, weather patterns, a number of different items. And MUSES is going to be a new platform that'll be open for use by a number of different entities, both commercial and governmental, for different applications, everything ranging from disaster response to general Earth observation to agricultural and land use to air quality, oil and gas exploration, just a number of different items. And MUSES, again, another one of those external payloads that was installed on the International Space Station after that successful delivery from Dragon. And then the third and final payload that was delivered in the trunk was the ROSA, the Rollout Solar Array. And this was a really fascinating study done in partnership with the Air Force Research Laboratory, testing out a new type of solar array. So having a very flexible material that came rolled up and then it unrolled almost like a party favor or a rollout tape. And then the array rolls and snaps open without a motor. So none of this was motorized. It was all stored energy just from the structure of the boom. So it was rolled out, and this was just a basic test of this type of technology. And they completed all of their science objectives in the week that ROSA was deployed on the end of the space station's robotic arm, actually in a position very similar to where we see Dragon right now, achieving all of their primary objectives and all of their secondary objectives as well. ROSA was originally scheduled to be installed back into Dragon's trunk and then disposed of along with the trunk, burning up in the Earth's atmosphere, but the teams hit a snag when doing some of the retractions. They were able to retract the array, actually retracting it 3 different times, but not able to get the latches just right, as they were seeing a little bit of differences in the alignment of the latches, but this is something that had been discussed pre-flight, and they actually ended up jettisoning ROSA from the end of the robotic arm, and it'll be in orbit for a number of months, ultimately burning up in the Earth's atmosphere, but not presenting any danger, obviously, to the International Space Station or to any of the other upcoming visiting vehicles. And again, although that latching didn't work, this is a technology demonstration, so the team's still learning. And the lessons that they learn from that, they're just going to be able to apply to these future designs. And this is just a really great example of all of these different types of technology demonstrations taking place on board the International Space Station, proving these technologies that are going to be used not only on the station, but in different spacecraft of the future as we look to explore even further beyond our own orbit.
Copy. Thank you.
So right now we are just about 19 minutes and counting from the opening of the release window. And again, once that release window is open, the crew can give the command to release Dragon. It'll take about a minute or so once the command is given for Dragon to actually be released, as a series of snares in the robotic arm execute and then release their grasp on the Dragon spacecraft. Pretty soon, Flight Director Dina Cantella going to go around the room, get a final go, no-go from the teams here in Mission Control Houston, radio that up to the astronauts waiting on board, Jack Fisher and Peggy Whitson inside the cupola at the robotics workstation. And then we'll continue to just stand by for the next couple of minutes until that release window opens and we get to see Dragon depart the International Space Station.
Did you want monitor 2 or monitor 1?
We'll take monitor 1, Peggy.
How does that view look?
And we're working on the routing right now. I'll let you know when we get it up.
All right, sounds good.
And Peggy, while we're getting that video routed, you have a go for Dragon configuration checks. Please perform step 1 in 1.602, Dragon departure monitoring.
Step 1 in 1.602, departure monitoring.
Again, continuing to get some pretty spectacular views of Dragon. This one actually from one of the newly installed HD cameras on the outside of the International Space Station. We're just under 15 minutes, actually 14 minutes, 42 seconds and counting away from the opening of the release window, at which point the crew will get the go to trigger the release of Dragon. Again, though, the teams here in Mission Control Houston will be going around the horn soon to get a final go, no go for the departure, and that'll be communicated up via Capcom to the Expedition 52 crew members on the International Space Station. So we'll stand by and just follow along and continue to get a few more great views of Dragon while it's still attached to the Canadarm2 and its mission still at the International Space Station.
Houston Station on 2. The dragging is providing LiDAR filter data from LiDAR 1, and light and CCP LED status are as expected.
So this actually a view from a camcorder inside the cupola. So this is actually what Jack Fisher and Peggy Whitson are seeing right now inside that cupola window. They're standing by again at the robotic workstation inside the windowed module for them to ultimately give the command to the Canadarm, to robotic arm, to release Dragon. And that release expected to come at about 1:41 a.m. Central Time. Spectacular blue ocean backdropping the Dragon spacecraft. The International Space Station actually just passing over the South China Sea, about to continue on this southeasterly track, eventually crossing over Indonesia and then over much of Australia before heading into an orbital nighttime. We're just a little over 10 minutes away from the opening of the release window. The teams here in Mission Control Houston go for departure, so we'll again just kind of continue to stand by here as we gear up to say farewell to Dragon. Jack Fisher and Peggy Whitson standing inside the cupola. They'll be the ones ultimately giving the command to release Dragon and send it on its way back home. And we are now 8 minutes and counting from the opening of the release window. Again, the window is going to open up at 1:40 a.m. Central Time. The departure expected to come around 1:41 a.m. It's because once the command sent, it takes about a minute or so before the robotic arm will actually release Dragon. But that departure could come anytime inside of the release window. It'll open up at 1:40 and it'll close at 2:05. In the event that they don't get Dragon off during this first release window, there is a backup window, but everything proceeding very smoothly so far this morning. Looking forward to an on-time release. And we are now under 5 minutes away from the opening of that release window. SpaceX Dragon, the CRS-11 commercial resupply mission, the 11th for SpaceX, getting ready to depart the International Space Station.
Station Houston on 2 for Dragon.
Go ahead on 2 for Dragon.
Okay, Peggy, we are looking good down here. You have a go for Dragon release on time. Perform steps 2 to 4 in 1.320 Dragon release. Your release window opens at 0640.
Go for step 2 and subsequent in procedure 1.320. Release window open at 0640.
Correction on the time, Peggy, and just to clarify, that's steps 2 through 4.
2 through 4 for steps in 1.320.
Good readback.
So we are just under 3 minutes away from the opening of that release window. You heard 0640, the station, and all the control teams around the globe operating on Greenwich Mean Time. So 6:40 in the morning for the crew on board the International Space Station is the opening of the release window. It'll be 1:40 a.m. here in Houston, 2:40 a.m. on the East Coast. The International Space Station is still a little over 255 statute miles, and it's just now crossing over Australia, so you should be treated to some pretty spectacular sights on the ground there as it crosses over the Northern Territory and then eventually swings out, crossing back over the ocean just to the south of Sydney. But we are just a little over 2 minutes away from the open of the release window. Again, once that release window opens, the crew will have the go to send the command to the Canadarm2 robotic arm to release Dragon. It'll take about a minute after the command is sent for Dragon to detach. It'll float away a short distance and then execute a series of 3 burns to begin taking it away from the International Space Station. Under 1 minute from the open of the release window. With that 1:40 a.m. Central, the release window is now open. So with the window open, we'll stand by for the issuance of the command to release Dragon from Canadarm2. And once the command's given, it takes a little while for the snares to retract and Dragon to be released, and then it'll slowly drift away. Getting the confirmation the snare's open. And as you can see, slowly moving away, Dragon released. And so the robotic arm now being backed away by the crew on board, and the release coming on time at 1:41 a.m. Central, while the station was a little over 258 statute miles over the central part of Australia. So they're now going to back the arm away, and then a series of 3 burns will be executed using thrusters on Dragon to begin taking it away from the International Space Station. Getting a good view right down the barrel of the robotic arm. You can see it continuing to back away. And the first departure burn has begun.
In Houston Station, Dragon depart was commanded, and we see VV mode departure.
Houston copies. Station, departure burn 1 is complete. Departure burn 2 in approximately 1 minute.
So the first departure burn good and in the books. The second one queued up next, taking place in just under a minute. That second departure burn will begin moving Dragon even further away from the International Space Station, setting it up for the third and final departure burn, which will eventually carry it out of what's known as the keep out sphere and the approach ellipsoid. These are basically distances around the International Space Station that govern interactions between the station and any other visiting vehicle approaching or leaving the orbiting complex. The visiting vehicle officer confirming the second departure burn has begun.
Station Houston, departure burn 2 is complete. Go for SSRMS safing. Perform step 5 in 1.320. You can expect departure burn 3 in approximately 7 minutes. Monitor per step 3 in 1.602.
Copy. Go for step 5 in 1.320, and monitoring step 3 in 1.602.
Good words, Peggy.
So Dragon continuing to fly away, the distance between it and the International Space Station to which it had been attached to for the last month continuing to widen. It'll have one more departure burn to finally get it out of the station's neighborhood and well on its way back for an eventual deorbit through the Earth's atmosphere. And SpaceX's Dragon, the only cargo ship currently capable of returning hardware back down to Earth through a splashdown into the Pacific Ocean. It's packed with over 4,100 pounds of vehicle hardware and science experiments and other items from the International Space Station.
Don, we'd like to say just a couple words for our friend that we just said goodbye to. Dragon's been an incredible spacecraft. I could even say it was slathered in awesome sauce. This baby has had almost no problems, which is an incredible feat considering it's the first reuse of a Dragon vehicle. And the science we've done, oh my, the science. Most of the 6,000 pounds of cargo carried was science, and almost all the return cargo are precious samples for discoveries we can't wait to see. In addition, Dragon brought up a host of external experiments. We've added an external platform for science, a neutron star analyzer, and a new solar array that rolled out like a party horn on New Year's Eve. The science of this mission has been nonstop, and we think the scientists will be extremely happy with the volumes of data we gathered for them up here in space in our floating world-class laboratory we call home. There are thousands across the world to thank, but a few big ones at SpaceX, Brian Coffey, Sarah Walker, and Artie Matthews, and at home in Houston, Kelly Holloman, Joey Crawford, Matt Wilkinson, Ryan East, Cal Ogden, and my buddy Dina Cantella, who put it all together. But really, for the whole SpaceX team, thank you for building us such a great vehicle and for finding us some good weather today to allow us to bring home the science on time. And for the worldwide team that makes our daily search for discoveries possible, thanks for letting us play a small role. Godspeed, air wins, Dragon 11.
Houston copies, and Two Fish and Peggy, nice words on behalf of the SpaceX and NASA team. Thanks for all of your hard work. It would have been possible without you.
Some eloquent words from the King of Awesome himself, NASA astronaut Jack Fisher, as both he and Peggy Whitson say farewell to the Dragon spacecraft, which a lot of the cargo on board has consumed their lives for the last month as they burn through thousands of pounds and dozens of different science experiments, many of which now making their way back down towards Earth, which you can see now shrouded in darkness. The International Space Station and Dragon just passing into an orbital nighttime, just crossing the Terminator line, that line between night and day on the Earth's surface. Dragon continuing to depart the area from the International Space Station. Coming up will be that third and final departure burn. We'll stick with it until it's out of the approach ellipsoid, that area around the station where vehicles coming and going from the station are closely watched and worked with the teams here in Mission Control Houston, but everything going very smoothly. An on-time release of Dragon at 1:41 a.m. Central Time, 2:41 a.m. Eastern, while both Dragon and the station were flying just over the central part of Australia. This, of course, setting it up for a splashdown in the Pacific, about 260 miles to the southwest of California. The splashdown time was pegged to be approximately 7:41 a.m. Central Time, so just about 6 hours exactly after the release, but that could of course change over the course of the next several hours. But that's the target time. It'll be 5:41 in the morning over on the west coast in California, where teams from SpaceX will be standing by to pluck Dragon out of the ocean, get it on a boat, and get it back into harbor to begin unloading all of that cargo on board. Again, a little over 4,100 pounds packed inside of the pressurized Dragon module, which will, in just a couple of hours, be making the plunge through the Earth's atmosphere, the heat shield protecting all of that critical cargo on board from the heat of re-entry, getting it down to a parachute-assisted landing in the Pacific Ocean for retrieval and delivery back to the coast. But everything going smoothly with this morning's operation. We'll just watch for a few more minutes while Dragon heads off into the black. Everything going very well with the end of this SpaceX's 11th commercial resupply mission. Getting confirmation the third and final departure burn has begun. Again, this just to continue getting Dragon out of the area of the International Space Station, putting it into its eventual deorbit attitude and deorbit positioning. That splashdown scheduled to come a little under 6 hours from now. Splashdown into the Pacific, where Dragon will get picked up by teams from SpaceX, but the third and final departure burn underway. Dragon soon will be out of the keep out sphere and the approach ellipsoid and on its way back to the Earth.
Burn 3 is complete. Dragon is outside the keep out sphere.
Station copies.
So again, Dragon now out of the keep out sphere. All 3 departure burns completed. We'll stick with it for just a few more minutes until it's out of that approach ellipsoid, and then we'll go ahead and say farewell. But everything gone by the book so far this morning. Dragon, which over the last several weeks has been packed with cargo and science samples bound for labs back down here on planet Earth. Over 4,100 pounds of stuff just inside of that Dragon module, going to be splashing down in the Pacific Ocean in just a couple of hours' time. It was the hatch was closed back on Saturday. Dragon itself was detached from the Harmony module, where it's been since June 5th. Just yesterday by teams here in Mission Control, and put into its release attitude, so its release positioning, and then Peggy Whitson and Jack Fisher inside the cupola giving the command on time at 7:41 a.m. Central Time, 8:41 a.m. Eastern, while the station was flying just over the central part of Australia and sending Dragon on its way. All 3 departure burns have gone flawlessly so far. It should be out of this approach ellipsoid in the next 3 or 4 minutes, and then Dragon will be well on its way. again, for now, we're just standing by. Just a few more moments. Should be hearing soon that Dragon is out of that approach ellipsoid, that area around the station, just signifying that it is outside of the station's immediate neighborhood and on its way towards its eventual splashdown. Should be hearing that momentarily. And there we hear it. The visiting vehicle officer confirmed Dragon outside the approach ellipsoid. It's release successful. It's on its way now towards that splashdown. Just to recap for you, SpaceX's Dragon, the CRS-11 mission, the 11th resupply mission for SpaceX, released at 1:41 a.m. Central Time, 2:41 a.m. Eastern Time, with 4,100 pounds of cargo on board. That release coming while the station flew just over Central Australia.
On 2, Dragon is outside the approach ellipsoid on a safe 24-hour free drift trajectory.
Aviation copies. Thanks for this update.
But with that Dragon now on its way, the splashdown scheduled around 7:41 a.m. Central Time, 8:41 a.m. Eastern, in the Pacific Ocean, about 260 miles southwest of California. Dragon will splash down, get picked up by a boat with SpaceX engineers on board, get brought back to port, and all of that cargo will get unloaded, with a lot of it being turned over immediately to get back in the hands of researchers down here on planet Earth to continue the research on their different experiments. But a successful mission for Dragon, splashdown up next, and then its mission will be at an end. But that's going to end our coverage today. I want to thank you for either staying up or waking up or tuning in, depending on where you are on planet Earth, and watching as we said farewell to this Dragon vehicle this morning. But with that, we are going to go ahead and end our coverage today. This is Mission Control Houston.
Welcome to NASA Edge.
An inside and outside look
at all things NASA.
Hey, we got a great show lined up today. We're going to be talking about 2 cool technology demonstration missions.
TDMs, we've covered them in the past, great ones, Deep Space Atomic Clock, Medley, LDSD.
LDSD or Space Bridge.
Yes, that's right, I like your phrase.
Yes.
But on today's show, we're going to be focused on GPIM and eCryo.
That's right, GPIM, which is the Green Propellant Infusion mission.
And eCryo is the evolvable cryogenics. And we're not talking about freezing somebody like in Star Wars with carbonite freezing. This is dealing with fuel.
That's a good point. You know, before we get to GPIM and eCryo, I had a chance to sit down with the Associate Administrator for the Space Technology Mission Director, Steve Jerzik, and I asked him how GPIM and eCryo fits into his portfolio. So Steve, we're talking about 2 really cool technology demonstration missions today, but before we get to those missions, let's look at the overarching theme for Space Technology Mission Director. What are you all about?
We run the cross-cutting technology programs for the agency, where we're developing revolutionary transformative technologies to enable the future missions for NASA. And we're really trying to enable not only more capable robotic missions, but also human exploration of the solar system. Our technologies cut across a lot of areas, and we have these 8 thrust areas, and they range from everything from advanced in-space propulsion to advanced power systems, to environmental control and life support systems, and even precision navigation. And so those are the capabilities that we're going to need, particularly if we're going to do human exploration of Mars.
Right. Now, we have 2 cool ones today. The first one, of course, is GPIM, or the Green Propellant Infusion Mission. Tell us a little bit about that and how that fits into your portfolio.
Yeah, so GPIM is part of our propulsion system portfolio. It is leveraging technology that was developed by the Air Force, which is a green propellant that is not only safer for the environment, but also provides higher performance for propulsion systems. So it's been a great partnership, not only with the Air Force, but with Ball Aerospace and Technologies Corporation and Aerojet Rocketdyne. And it's just an example of a very cross-cutting technology. You know, one that can be used in not only spacecraft developed for NASA missions, but missions for other government agencies and the commercial industry in general.
And the other technology demonstration mission is eCryo. Where does that fit in your portfolio?
Yeah, so that's also a propulsion system technology, completely different though. What we're trying to do is a couple of things. One is hydrogen and oxygen are very low temperature. And if you don't insulate them in a system, they boil off and it just goes away. You can't fill the tank up fast enough to keep it full. So we're trying to develop technology to insulate the system so we can store propellant in orbit. And then we're also developing technology to transfer from a delivery spacecraft to another spacecraft. So this gives you operational flexibility. You can have upper stages stay longer in orbit and refire them for more mission agility. And also it's part of our architecture to launch systems and reuse them in space.
Right.
So you use up the fuel, but it stays in space. You send up a fueling system and you refuel them and use them again.
So is it fair to say, Steve, that in STMD, you're looking at technologies that maybe relatively new, that you're just starting out maybe as a paper study, but then you have some technologies that are more mature that are ready for spaceflight?
Yeah, so our programs are organized like that. So we have a set of early stage programs, space technology research grants, or research with universities. So that tends to be what we call lower technology readiness level. And then we have what's called NASA Innovative Advanced Concepts. And we do a solicitation every year, and we get proposals from everywhere, NASA centers and universities and industry. And we get some really interesting kind of way out concepts, things like laser propulsion and mining asteroids for fuel and water. And so not many of them go on to the more mature projects, but it's really great to see the innovation that we get. And then we have the game-changing development program, which takes some of those ideas that are kind of way out there and matures them.
Right.
Then the ones that pan out of game-changing move on to technology demonstration missions like GPIM and eCryo.
So you're the guy to go to if someone has invented the lightsaber, warp drive.
Yep, we're always looking for warp drive. We're always looking for warp drive, infinite energy at zero mass and zero volume. Those are all the things we're always looking for. And so, yeah, if somebody has unobtainium out there, we want it, yeah.
Look, guys, I got to say, you know, I really enjoyed talking with Steve, but he lost me in that last part, unobtainium. I'm not down with the times.
Well, I mean, you know, it's a good reference. It's a reference to Avatar. That's what they're mining on Pandora.
Okay.
So I give Steve a little bit of credit for
Showing
actually
us his sci-fi chops.
Yeah.
I mean, I would have said vibranium, adamantium, and that's more, you know.
Yeah, you're on that Marvel line.
Yeah.
You know.
As interesting as Marvel is, and as much as we love them, the technology we're going to talk about today, though, is still very cool and not, hopefully, unobtainable, but very attainable. Green propellant. It's green in that it's environmentally friendly, or friendlier than what we currently use. But the real expert on green propellant is Chris McLean at Ball Aerospace, and I had a chance to sit down with him and get all the details about the green propellant infusion mission. So Chris, I'm very excited about this green propellant infusion mission, but what exactly is green propellant?
Well, green propellant is a non-toxic fuel, relatively speaking, compared to heritage in-space propulsion technologies like hydrazine and hypergolics. What makes it really green is the fact that it has a very low vapor pressure. You can put a container of this stuff on your desk and there is no evolution of nasty species that might mess with your breathing and, you know, get into your airways and stuff. And it actually, the toxicity of the liquid itself is really low. It's something you could almost drink, but not quite. We're also able to ship it at FedEx across the country. We don't have to have it in explosion-proof containers.
Could you, say, ship me some green propellant for my desk back at NASA?
Well, that's a nice idea, and we've been asked to do that before. However, it is still an explosive.
Oh,
so
well,
even though it has a low explosive handling rating for shipping, it's not something you'd probably want sitting around all the time. So
obviously, that has good. It's good to be green and obviously conscious in that way here on the planet. What kind of benefits does that add for space travel?
The green benefits aren't really part of the space application, right? It's for when we're handling it and loading it and providing protection to the technicians and engineers that work with this stuff. When you're working with this fuel, you really don't have to worry about exposure to it. If you spill some, you can clean it up with water and rags and things like that. When we're in space, the real benefit is the performance of this fuel. There are two things about this propellant that make it outstanding compared to heritage fuels. One is the performance is significantly better for a monopropellant. If we look at a hydrazine system, which is similar to what we're doing here in terms of a single fluid and rocket engines attached to that, this thing has 50% better performance. So if you can imagine your car had enough gas in a fuel tank to go 100 miles, well, for that same fuel tank, you go 150 miles with this fuel.
You've basically turned it into a hybrid vehicle.
All right, pretty much. And some of the other benefits are when we look at deep space missions, there are times when with a hydrazine system, you need to have heater power going all the time to keep the propellant from freezing. Because if it freezes, if hydrazine or any of the traditional propellants freeze, it expands like water, like ice in your ice cube tray, and it'll break lines and things like that. With this fuel, it goes through a glass transition phase and does not expand at all. So for certain power critical applications like going to the South Pole of Mars, which is an example, or landing on a comet, if you wanted to be there for a while, you could save energy and put it into the electronics and things that need that energy and not spend the resources keeping the fuel liquid, because you don't have to do that.
So what exactly is infusion of the green propellant infusion mission?
When we look at technologies that are employed on spacecraft are high dollar assets, but especially the big geocoms. You can talk $500 million or more for an asset like that. So in order to use a technology like this and take advantage of the performance benefits that are offered by it, you need to demonstrate that first. Almost every spacecraft that you will look at, they'll say, well, has this flown before? What's its history? What's its heritage on orbit? What is our experience base with it? So by flying this technology on this spacecraft, we build that experience base. A lot of it, in my mind, which kind of surprised me as I went through this process, was realizing, getting range safety familiar with it and the loading people saying, hey, this is a new fuel. We haven't had a new fuel go through some of the processing steps since 1972. So by the time we're done with this mission, we'll have characterized this fuel on orbit on a spacecraft, demonstrating that we can do all of the heritage applications of propulsion for a spacecraft, of moving it around, desaturating momentum wheels and pointing the spacecraft and things like that. And so we can say, hey, this technology is ready. It's ready for use on other applications. And as people start proposing spacecraft downstream, they can say, hey, they're in my catalog and my toolkit of things I can put into this proposal, into this spacecraft. Green propellant's been demonstrated, so we can use that.
I think this could be the first time in my recollection that the word green is used.
You sure?
Hey, he's really struggling with his certainty on this.
I think this is the first time that the word green is used in conjunction with a space technology. Is that fair to say?
I think that is fair, and additionally, all of the environmental benefits of this mission really take place here on Earth, but when they go to space, they're not compromising any performance, which is really awesome in terms of this being a good technology to be developed by NASA.
And speaking of going to space, we're actually going to cover the launch of GPIM along with the Deep Space Atomic Clock next year on a live show.
Yeah, I'm looking forward to that because I think that launch is going to take place down at NASA Kennedy, which we love covering launches live, don't we?
Sure.
Yes.
Now, speaking of technology, we talked about GPIM, great technology, but now we have to shift gears. We have another technology we need to talk about, which is evolvable cryogenics.
Right, and I had a chance to sit down with the eCryo program manager and my genius twin brother, Hans Hansen, to learn all about the many aspects of eCryo. So Hans, I noticed you have a lot of moving parts in the eCryo program, but there are a lot of things that are this or that, so I'm wondering what exactly is eCryo?
Sure. So eCryo is evolvable cryogenics. So we're looking to try to build on cryogenic fluid management technologies, or CFM, for in-space applications that can be scaled up to an upper stage or potentially a depot down the line, or even Mars applications. We're looking at either demonstrating technologies for the first time, or how can we scale it up to a larger scale so that it can be infused into a mission.
Now, Hans, correct me if I'm wrong, but I always understood cryogenics as sort of that process where you freeze the astronauts so that they can live longer in space on their trip to Mars. That's not what's going on here.
No, we're not looking at cryogenics for that application. We're looking at it for...
So there is an application to do that. So, I'm sorry, go ahead.
We're looking at using cryogenics in storing fuels. So the reason we use cryogenics is they have a very high energy efficiency so that you can get the most bang for your buck, or best gas mileage, if you will.
It's important in space too, I guess.
Yeah, especially in space, because every pound matters. So what we're looking at is to try to see how can we be more efficient with storage of these fuels, because they have to be stored at such a cold temperature. We're trying to prevent the fluids from boiling off so you don't lose your fuel on your way to your mission.
Now, I was looking at your logo and I noticed you have a veritable plethora of acronyms there. Maybe it should be E-acronyms as your title.
Yeah, we have some talented team members who came up with a bunch of these acronyms, but yeah, our modeling effort is DVAT. It's development of and validation of analytical tools. That's where we're doing our modeling and simulation of the physics. We're also working on IFUSI, it's improved fundamental understanding of super insulation. So we're looking at a coupon level multi-layer insulation technologies that are used on spacecraft and upper stage tanks for long duration missions to try to extend the mission duration from a couple hours to maybe potentially even months if you're going to a Mars application. Shiver is our largest element of our project. It's a 4-meter tank where we're going to be testing liquid hydrogen type applications applicable to an upper stage.
Now, what about RFMG? What's that all about? I tried to guess, but I can't quite get a handle.
RFMG is our radio frequency mass gauge. Once you get up in space in microgravity, you don't have a level sensing opportunity, so we're trying to use radio frequency to gauge how much fluid is in a tank.
You definitely want to know how close you are to E when you're ready to head back from Mars, right? What about IVF?
So IVF stands for Integrated Vehicle Fluids. This is a ULA-based proprietary technology that we're looking at doing some testing and assessment of the technology to see if it's applicable for the Base Launch Systems exploration upper stage. We're doing testing and analysis and modeling to see if it could save potentially a few thousand pounds up mass for the SLS program.
So essentially what you're saying is if eCryo is successful, that eventually we'll have a lean, mean spaceflight machine.
Yeah, we're trying to get as efficient as we can with our fluid management. The whole eCryo project is trying to understand how fluids operate in a microgravity environment.
One of the things that Hans also said is they're trying to get this technology to the point where they can actually test it in space, because once you know that the technology actually works in flight, then it can be a part of every NASA mission coming down the line. And that's really the goal of these technology demonstration missions.
And just like Hans said...
Oh, wait a minute. I'm sorry, forgot. I gotta mention this because Hans, my twin brother, actually told me that I needed to be sure that I made this point. Okay, I made the point in the interview. It's ridiculous. NASA's explicitly not involved in cryogenic research of that kind, which is ridiculous. But then last night, I was thinking when I couldn't sleep, I was like, e-cryo, think about it in sci-fi, never a good idea. Not once do you watch a sci-fi movie where they have cryogenic sleep and you think, man, that's technology we need. It's always problematic, right? So not only does NASA not do it, but it's not even really helpful in the sci-fi community, right?
Continuing on. So if you remember in his interview with Hans, eCryo has a bunch of smaller projects that are kind of under the umbrella of eCryo.
That's true. That is true.
And one of them is called Shiver. And I had a chance to talk with Monica Guzik, the lead engineer for Shiver. And the cool thing about this, we had a chance to go out to the Plum facility, which is about an hour from Glen, in a building called B2, where they had a thermal vac chamber. So Monica, shivers. Every time I hear that, I get cold. What's that all about?
Well, we did that on purpose.
Okay.
We're dealing with very cold stuff. We're actually dealing with cryogenic liquids. But SHIVER stands for Structural Heat Intercept Insulation and Vibration Evaluation Rig.
Okay, that's a mouthful, so you're gonna have to explain that to me.
So what's going on here is we've got, liquid rocket propellant tanks, and they're cryogenic, which means really, really cold.
Right.
And we're storing cold liquids. So what happens when you have a cold liquid is anytime you get heat in, you start boiling it off, just like water on a stove.
Okay.
For us, boiling off is not a good thing because that means that we're losing fuel. Imagine trying to go drive to California with a leaky fuel tank and no gas stations in between. We're never going to get there.
Okay.
We have the same situation, so we're trying to plug that leak by preventing the heat from coming in.
And what are you using to prevent that leak?
So we're doing it two things, and that's right in the name. We're using structural heat interception, which means that we're actually cooling the structures. These tanks have to be held up by something, and they're attached to really hot parts of the spacecraft.
Right.
So we're trying to cool those attachment points so that we reduce the heat coming through them. We're also using insulation to try to prevent radiation that's coming in from the surrounding space environment.
So now what kind of materials do you use to insulate the tank?
What we're using primarily is called multi-layer insulation, or MLI.
Right.
So once you're in orbit, you don't have air or anything hitting it. Your primary source of heat is what we call radiation.
Okay.
The radiation is heat coming in from a really hot source and kind of transmitting from that source to a surface.
Right.
We prevent that by using highly reflective sheets. You can think of it as almost like a mirror. They're reflecting that heat away and preventing that heat from getting in. So we have layers of what we call mylar, which is actually just a type of really, really thin plastic.
Right.
And we coat them with aluminum or some other reflective material on both sides. And they end up looking a lot like really, really thin tin foil.
Okay.
And we layer these up and we separate each layer by something that doesn't conduct a lot of heat and is really lightweight. And it actually looks like the veil material that a bride would have on her wedding day.
I guess what you got to determine is how thick that insulation is around the tanks?
Right. The more layers you add, the less heat can get in, but that means you're also adding more material, which is more mass.
Right. So there's a trade-off.
There's a mass trade, right? Because mass is money when we launch, so we're trying to save mass without adding too much.
I mean, I can only imagine when the launch vehicle is taking off from the pad, it's shaking, it's vibrating. I mean, there's a chance that material can come off.
Yes, there is.
So do you have to do testing to make sure it stays on, or?
Yes, we do. And that's the vibration. The VER part of it is the vibration evaluation that we're looking at.
Right.
So what we're going to do first is we're going to test here in this B2 chamber.
So this is a thermal vac?
This is a thermal vacuum chamber called B2.
Okay.
And so here we can test very large. We've actually tested full rocket stages here before, and it actually is capable of live firing rockets, although we're not going to do that here. We're going to keep everything from burning up.
So how do you actually do a thermal test? If I put your simulated tank in here, you got to close the door somehow, and so how do you heat up the temperature so it's in space conditions?
Right. So one thing that's funny is since we're so cold, actually just the temperature right now will heat up the tank.
Oh, wow.
So when we talk about it, we're going to take this tank, we're going to close it, and you can sort of see the top of what we call a cryo shroud behind me. And what we do is we can run either liquid or gaseous nitrogen through the tubes that are embedded in the shroud. And those tubes we can set so that they're a certain temperature that mimics what we'd encounter in a space environment. And it may, in fact, be colder than the air around us right now, but it's still very, very warm compared to the liquid in that tank.
You're not really worried about the thermal test on launch, though, right?
Right.
This is more of in transit.
Yes.
Okay, but then on launch, you're worried about vibrations, acoustic noise, things of that.
So once we do our first thermal test and we see how does it perform, you know, when we know it's working, when it's good, it hasn't shook or anything, we're going to take it over to our facility called the Reverberant Vibroacoustic Test Facility. And we put it in there, and there's a whole bunch of what look like big speakers on the wall, and they can emit vibration sounds, acoustic sounds, to the levels that we'd encounter in launch.
And that would be typical for the launch vehicle that it's going up on.
Exactly. Yes, and we actually have some of those launch profiles already, and we're going to use those when we do our testing with the Shiver tank.
I tell you what, it seems like the Shiver is an extremely important program for the journey to Mars, because if we want to send humans to Mars one day, we don't want boil off, we don't want to lose the propellant. And so really you have a critical role to making sure that there's enough propellant to get to your destination.
Definitely, yes. You can imagine if you were trying to go somewhere and you run out of fuel halfway there. It's bad enough if you're in the middle of nowhere, you know, in the country, but it's really bad if you're in the middle of space on the way to Mars. So you definitely need to make sure you have fuel in the tank there and back.
So as I was processing this interview with Monica, as I was looking at it, as I was evaluating, I kept thinking with this idea of boil off, this kind of cold, kind of boiling in space kind of temperatures, I was thinking, well, that doesn't make sense to me because water like boils at 100 degrees Celsius, and that's like hot, right? So that's hot, it's very hot, but it's very cold in space. So I'm wondering, how are things boiling off in space? Is there something on the spacecraft that's so hot? I may have missed it. She may have addressed it, but I'm just curious if you dealt with this.
Different liquids have different boiling points. So just like you said with water, water boils at 100 degrees Celsius or 212 degrees Fahrenheit, right? So we're talking about cryogenic fuels. We're talking about really cold temperatures, you know, in the minus 300 to 400 degrees range, right? So it doesn't take very much to boil those liquids off. So if you have something a little bit warmer than that, it could boil off.
So warmer is a relative term, warmer than that extremely cold. So from going from extremely cold to just slightly less extremely cold equals boil off.
This is where the multi-layer insulation comes in, because you have to make sure that you maintain that temperature inside the tank so that you don't get that boil off.
And so you just keep like slapping layer after layer after layer after layer after layer on there until you get that sucker nice and, you know, comfortable, so there's no uncomfortable boil off. So, okay, I got it. Now that's interesting, right? That's a total interesting topic. Here's another question, because I'm wondering if you're curious like I am. Have you ever wondered, especially if we're talking about fuels, you ever seen the ISS when the astronauts are up there and they've got the little water droplets and they're floating around and everything? And it's cool, right? It's fascinating. If you ever wondered, what happens to the fuel in the tank? When it's full, I get it. You know, there's no room for anything to move around, but as you start to use that full, does it turn into little globs and start floating around inside the tank? Does that happen? Is that possible?
That's a great question.
Exactly, which is exactly the question I brought up with our good friend Greg Zimmerly, who's actually working on a technology to find out how to measure fuel inside a tank when it is floating around inside there. Let's check it out. Greg, before we get into the radio frequency element of your program, I'm just curious, I understand there's a challenge in measuring the quantity or amount of fuel in a tank in zero gravity. What is the challenge? What's exactly going on here?
Well, in 1G, or in Earth's gravity, the fluid settles to the bottom of the container, so we're able to use what we call a level sensor to sense how much liquid is in the tank. But in zero gravity, surface tension forces, other things like that, they can move the fluid around inside the tank to places where you're not sure where it's going to be. So we're working on a technique that can measure the quantity of liquid in the tank no matter where it is.
Now, correct me if I'm wrong, and believe me, most of the time I am, but it seems like it'd be kind of tricky to put anything that emits any kind of frequency in a fuel tank, because it might be, you know, combustible or something. How are you accomplishing this?
The technique we're using, the radio frequency mass gauge, we put an antenna inside of a tank and we transmit a range of radio frequencies through the antenna. Those frequencies emit radio waves inside the tank, and it creates modes, and natural electromagnetic modes inside the tank. And we measure those modes with a special instrument. It's very low power. There's no dangers with the technique.
So have you done any testing on this technology so far?
We have. We've done a lot of testing here at Glenn Research Center. We've tested the technology in liquid hydrogen, liquid oxygen, liquid methane. We've also tested it on the parabolic aircraft.
Yeah, that's for the lower gravity situation.
The low G, right. So we get to about 20 seconds of low gravity on the parabolic aircraft. We weren't using the cryogenic fluids there. We were using a room temperature simulant fluid for those.
Well, now it's interesting you mentioned all those different test fuels. Did they behave differently in zero G?
In zero G, they'll behave a little bit differently because the surface tension of all those fluids is a little bit different. For example, water has a very high surface tension. but liquid hydrogen has a very low surface tension. So in that respect, they're different. But the only real difference for the radio frequency mass gauge is a property called the dielectric constant, which is...
All right,
well,
so you just
I
moved
guess.
above my grade of understanding, but...
Maybe I should say the index of refraction of the fluid. For example, glass and water slows the speed of light at different rates, for example, okay? So these fluids also slow the speed of light in a known way, and that's called the index of refraction of the fluid. So the radio frequency mass gauge is sensitive to that index of refraction. It slows down the speed of light. It changes these mode frequencies of the tank in a way that we can predict. So we measure those frequencies, and then we compare those to some simulations that we do on the ground ahead of time. And then we use it's almost like a digital fingerprinting matching technique, okay? So we compare the spectrum of the tank that we measure with what we've calculated, and we find the best match, and then that tells us approximately how much fuel is inside the tank. The technique actually, it works relatively quickly. We can gauge a tank in a few seconds, for example. So you could gauge it as often as you want. You could have a real-time gauge that's showing how much liquid is in the tank.
But this is really exciting. I love this, but I'm curious now, how are they measuring it now?
So for the cryogenic propellants, there is no way currently to measure how much fuel is in the tanks when it's in low gravity. So we have to resort to secondary techniques that we call bookkeeping, for example. So we know how much fuel we started out with or how much propellant. We know how much we've used when we do engine burns, things like that. So it's sort of an accounting technique. So we call it the bookkeeping technique.
Wow. So it seems like this technology will actually go a long way and not just being more efficient, but giving a lot of confidence to mission planners in terms of knowing how much fuel they need and how much they have at any given moment.
That's right. It's sort of an enabling technology.
Is it fair to say that as you increase the size of the tank, you scale it up, that you would have to put more antennas inside the tank?
Scale up more antennas. My first impression, just based on Greg's expertise and everything I listened to in the interview and just my overall thoughts of the whole process would be, no more, and you don't need more antennas. What you really need, bigger antennas. Scale up, bigger antennas. You don't need more antennas, just bigger antennas.
Okay, as we wrap up the show, we talked about two great...
Wait. Before we get to the end of the show, I've got more stuff from our good buddy Hans, who's got more information.
Okay, go ahead.
So Hans said he had some very key information, and I was supposed to mention it earlier, and I think I did, but I don't think I did a good enough job, so I just want to go through it real quickly here. He says that, all these things in eCryo and the various parts like Infusey and Shiver and DVAT, which is a modeling component that we did not talk about. These are not just like all similar groups that are studying. They're studying it at different phases. So here's what he says. He says they're testing at the coupon level with Infusey. That's a smaller level. They're doing scalability with Shiver, and then they're performing predictive modeling with DVAT, all moving toward getting that space test eventually so that it can be proved in space and therefore put in future missions. Thank you. Through email, last-minute communication, nailed it.
Okay, so as we wrap up the show, we talked about GPIM earlier in the show, and remember in an interview with Chris McLean that...
Great guy. Great guy. Looks like the bad guy in Heroes. Remember the guy with the glasses? The cheerleader turned out being a good guy.
So remember that Chris said that he couldn't get a hold of some green propellant from Fusion Mission?
Right.
It's peachy color.
Right.
What is that on the table?
What is that?
This, my friends, energy drink. I was concerned that I would not be able to perform to scalability with these TDMs, so I went out and purchased an energy drink, so I would have the caffeine to do well in the show today.
So that's not GPIM. I just want to clarify it, because you can't drink it.
Nobody can drink GPIM. That's bad. It's like not healthy. It's something that you could get close. You could spill in a shop and wipe up with a sponge or something like that. But you wouldn't want to make it a beverage on like a drink list, or you wouldn't want to bring it to parties, or you wouldn't want to offer it to your friend, or you wouldn't want to give it to someone who's thirsty, because that would be cruel.
Are you done?
I could be.
You're watching NASA Edge, an inside and outside look at all things NASA.
That better not be GP.
Oh, no. It's just an energy drink. Who would drink green propellant? It's not good for the environment inside your body. It's like bad. It's not green for the intestines.
Hey, you're watching NASA TV, on the air and online every day, on this planet and beyond.
Here's some of the stories trending this week at NASA. President Donald Trump signed an executive order on June 30th to reestablish the National Space Council. Vice President Mike Pence, who will chair the council, was on hand for the signing, along with members of Congress, NASA representatives, commercial space company officials, and others. Acting Administrator Robert Lightfoot called the establishment of the council, quote, another demonstration of the Trump administration's deep interest in our work and a testament to the importance of space exploration to our economy, our nation, and the planet as a whole. June 30th marked International Asteroid Day. Our Planetary Defense Coordination Office and other NASA-funded programs find, track, and characterize near-Earth objects. These are asteroids and comets in the vicinity of Earth's orbit that could pose an impact threat to our planet. The Planetary Defense Coordination Office also issues alerts and helps coordinate any U.S. government response to an impact threat. Our acting administrator, Robert Lightfoot, and other NASA officials testified at congressional subcommittee hearings on June 29th. Lightfoot responded to questions during a Senate Appropriations hearing about the president's $19.1 billion fiscal year 2018 budget proposal for NASA. Meanwhile, Bill Gerstenmaier, the Associate Administrator for Human Exploration and Operations, and Steve Jerzik, Associate Administrator for Space Technology, testified during a House Science hearing about in-space propulsion. On June 30th, we launched a sounding rocket from our Wallops Flight Facility in Virginia to test a new multi-canister ejection system designed to help study the ionosphere and aurora. The system produces blue-green and red artificial clouds or vapor tracers that enable scientists on the ground to visually track particle motions in space. The colorful clouds from this launch were expected to be visible from New York to North Carolina. And that's what's up this week at NASA. For more on these and other stories, follow us on the web at www.nasa.gov.
Going through my whole life, I've never necessarily been the smartest guy or the fastest or the best pilot, but I could always outwork anybody. So I came from what was then a small town, Louisville, Colorado. The fifth generation of Fisher to grow up in that town, and everybody had been a contractor. You know, on the construction site, there's one goal, and that's to get the job done. So I was the smallest, the youngest of the 4 kids. Dad always said, well, you're not worth much on a shovel yet, but I'll put you in the Bobcat. I was always the kid who was driving the tractors and the trucks and the trailers and everything, and I was also the one who would upkeep them. At night, I would stay late and I would clean them and I would change the oil, and I loved my machines. And really that has followed me through certainly as a pilot and now as an astronaut, working with machines and being kind of in tune to how they're operating and what you need to do to get them at their peak efficiency. I think that has followed me my entire career. When I was 6, there's actually a picture of me and my siblings. So we're right next to the Saturn V. You know, I just looked up at this ginormous rocket and fell in love with the whole idea. I really chased that dream as I grew up and wanted to serve my country, went to the Air Force Academy. But it wasn't until my sophomore year at the Air Force Academy where it really became a passion. My dad was dying of cancer, and I had gone home kind of on his last bit of time, and I said, Dad, I'm gonna come home. I want to help with the family company, and I just feel like I'm in the wrong place up there. He's like, man, your head has always been in the stars, and there's no way you're coming home. I dare you to dream. For me on the launch, you know, I'm gonna go to work, I'm gonna get to orbit, and as soon as everything deploys and we're happy, I'm gonna look out that window and just take a little minute and enjoy that moment. I will be thinking about, probably thinking about Dad. He was gone before I became who I am. You wanted him to see you become something. And so, I'll be thinking of him. I'm Jack Fisher, and as an astronaut, I'm just one small part of the overall effort to explore space.
It is often said that the only thing constant in life is change. That is as true at NASA as anywhere else. But the men and women of NASA generally see change differently than others because their life's work is all about change. Through their tireless efforts, these talented professionals move past the status quo every day and help us understand and change our world for the better. But even though change is part of their job requirement, the people of NASA understand that all projects eventually come to an end, and they will have to transition from one assignment and get ready for their next challenge. That transition is beginning to happen now for the members of the Environmentally Responsible Aviation Project. After 6 long years of study, team members are closing the books on the ERA research project that has provided so much new information about how future aircraft will fly. This team has worked diligently over the past half-decade to reduce aircraft drag by 8%, reduce aircraft weight by 10%, reduce engine-specific fuel consumption by 15%, reduce oxides of nitrogen emissions of the engine by 75%, and to reduce aircraft noise by 1/8 compared with current standards, all by the year 2025. These were stretch goals to be sure, but not surprisingly, their efforts have paid off for all of us. Today on NASA X, we will look at part 2 of this 2-part program that has explored the work done by the ERA team. We will look back at some of their early work while also looking at what some of the finished products look like. We will see how NASA and industry have worked together to improve the state-of-the-art for aircraft design, and we'll find out about promising new ideas that have come out of this work. Finally, we will bid farewell to the team that is changing the way we all fly. Created in 2009 as part of NASA's Aeronautics Research Mission Directorate's Integrated Systems Research Program, the Environmentally Responsible Aviation Project was tasked with exploring and documenting the feasibility of vehicle concepts and enabling technologies to reduce aviation's impact on the environment. Aircraft have benefited greatly by the work done by NASA engineers over the decades, but with changes in technology, NASA knew that much more could still be done. The ERA project was organized to mature promising technology and advance aircraft configurations that meet midterm goals for community noise, reduce fuel burn and nitrogen oxides or NOx emissions. They were also tasked with determining the potential impact of these advanced aircraft designs and technologies into the air transportation system. They have done all this and more. The solutions that they have achieved will undoubtedly reduce fuel consumption by up to several percentage points for the aircraft community. That may not sound like much, but shaving aircraft fuel consumption even a few percentage points can save millions of dollars and help protect the environment from harmful emissions. One area that the team focused on heavily to meet these goals was to develop, in collaboration with their industry partners, a new type of aircraft called the hybrid wing body concept. NASA planners did early wind tunnel tests and scale model tests with great success. The final phase of this testing is being done here at NASA Ames Research Center's 40 by 80 tunnel in California. The INFAC is actually home to 2 interconnected wind tunnels. One test section, the world's largest, measures 80 feet tall by 120 feet wide. The other one, the world's second largest, has a test section that measures 40 feet tall by 80 feet wide. This full-scale tunnel has been used since World War II and has helped perfect numerous aircraft designs, and is now being used to help with this unique aircraft. Here is Kevin James from NASA Ames to explain.
If you take an airplane from, say, 1950, and you take an airplane from, say, today, and you lay them on top of each other, they have almost exactly the same outline. And there've been a lot of improvements, but as we start looking for something that's dramatically different, where you're really going to make improvements in fuel economy, fuel emissions, and acoustics, say community noise and the impact that we have on how people live their lives, we have to keep looking and sometimes think outside of the box. So this is a hybrid blended wing body. We call the generic airplanes of today tube and wings. And that sort of makes sense because they're just a big old tube with a wing on it, and we all just go along for the ride. What we've done here is we've actually taken that tube, and with the abilities that we've had in improvements in structures and materials, specifically composites, we can now go from a tube shape to more of an elongated shape, because the pressure vessel wants to be a tube and we want to kind of stretch it a little. Well, when we stretch it and then we blend the wings into it, we get this hybrid blended wing body airplane. And through very careful control of weight and very careful configuration control, including how you put the engines on it, we have significant improvements in fuel burn and also very significant improvements in noise. Our mandate was a 50% reduction in fuel burn, gate to gate, and a 42 decibel reduction in noise in a cumulative fashion from a 1999 Target airplane. Where we ended up was really, really close. We made over 48% improvement in fuel burn, so missed it by just that much, and really close to we're at 40 dB down. Cumulative. But a good way to keep in mind what that really means is every 6 decibels of change is a doubling of the noise, our perception of the noise. So when we start talking about numbers like 42 dB down, even if it's cumulative, that is a huge improvement. What that really is in terms of quality of life for people in cities, especially around airports, is a significant improvement to what they've come to expect. It's been a lot of hard work. There's always frustrations, but that's kind of what makes the job fun sometimes, is solving the challenges. We have worked with some phenomenally good people. We are really truly blessed. NASA has hands down the best people on the planet. Just really good people. Smart, interactive, social, full of good ideas and wanting to solve problems. It has been a lot of fun seeing the pieces all come together, and ERA was laid out in a really kind of a very slick way. You've got the vehicle and the systems integration, you've got structures, and you've got the engine and propulsion. And again, to meet the stated goals, all 3 legs had to deliver. And as we get to the end of the program, it is just incredible seeing the progress that was made and the deliverables that we're getting from all of the components. And as they come together, you see that we are actually going to be able to be in a position to say something like this works. And this is where we should be headed.
The research from the hybrid wing-body aircraft will continue. And one day, in the near future, we may all see these types of revolutionary aircraft flying in our skies. Another concept the ERA team has been working on, called Active Flow Control Enhanced Vertical Tail Flight Experiment, has shown much promise as well. The ERA team worked in cooperation with Boeing to develop a plan to test this innovative idea in the wind tunnel and on an actual aircraft in flight. Before flight tests were done, the team installed 31 sweeping jet actuators onto a tail section of a 757 aircraft. These jets can manipulate, on demand, the air that flows over the vertical tail and rudder surfaces. This test is important because it has the potential to reduce the weight associated with the tail section. An aircraft's vertical tail is primarily used to add stability and directional control during takeoff and landing, especially in the event of an engine failure. But when the aircraft is cruising at altitude, the same large heavy tail is not necessary. Engineers theorized they could reduce the size of the vertical tail by using the sweeping jets to generate the same side force during takeoff and landing. That would reduce both the weight and drag of the airplane and decrease its fuel consumption. In order to test this large tail section, the team had to place it inside the NASA facility that is home to the world's largest wind tunnels, the National Full-Scale Aerodynamics Complex, or NFAC. Ground studies by a team of NASA, Boeing, University of Arizona, and Caltech researchers on this full-scale 757 vertical tail in the NFAC did in fact show that the active flow-controlled jets could potentially increase side force by as much as 20 to 30%. That low number of 20% increase in side force could allow designers to scale down the vertical tail by about 17% and therefore reduce fuel usage by as much as 0.5%. But this is not the only potential benefit. In addition to reduced weight and fuel economy, this type of device could also allow for new aircraft to use shorter runways. Here is the man who is called the father of active flow control, the University of Arizona's Iggy Wignansky.
We can possibly take off from a football field size with some sort of a rotor type airplane, maybe partly tilt rotor, partly tilt wing. And we can fly possibly at 350 to 400 knots and do this very efficiently. So since most of our flights are of the order of 1,000 miles, if you do it from downtown to downtown, from a parking lot to another parking lot, that's much more effective than to do it the way we do today. Because on a distance, let's say from here to Tucson, I spent about 2 hours at the airports, and this is not really necessary. And there are a lot of, by the way, small airports of runways that are less than 5,000 feet. Are in a lot of city centers or close to city centers that can be utilized and can be utilized effectively. So some sort of short takeoff airplane that would use this technology could be very effective.
After testing on the tail was complete at the NFAC, NASA and Boeing placed the tail on a Boeing test aircraft called the Eco Demonstrator. This aircraft is unique because it is being used as a flying test bed to evaluate different technologies that could increase efficiency. With the active flow tail attached, testing continued back at Boeing Field, with much of the research data being validated in flight.
Building on that 100-year collaboration we've had between NASA and Boeing, the Eco Demonstrator program really is about continuing that legacy and spurring some more action to see that continued collaboration together successfully.
This collaboration and testing is important, not only because technology must move forward, but because of the significant savings this could potentially afford aircraft operators and the flying public.
When you think about the worldwide fleet of airplanes, there are about 18,000 airplanes that fly today. And it's projected to grow to 36,000 airplanes in the next 20 years. So if you can get a little bit of improvement on one airplane, and it's multiplied times 36,000 in the next 20 years. So it's huge improvements with regard to reducing overall fuel burn.
Having a relevant test bed like Boeing's Eco Demonstrator is helping to mature technology concepts that have been extremely important to NASA's environmentally responsible aviation project. Researchers have been working hard to develop technologies to reduce airplane fuel consumption, noise, and emissions. Being able to prove those concepts in flight tests gives them a better shot of getting into the commercial fleet. Because the eco-demonstrator was designed to test multiple experiments at once, Boeing and the ERA team also decided to test special material coatings on the right wing of this aircraft that could reduce bug contamination. This test was called the Insect Accretion and Mitigation Experiment, which in layman's terms means that it is simply an experiment to test how to keep bug guts from reducing aircraft efficiency. It might seem odd that NASA would spend its time worrying about seemingly innocuous bug strikes, but believe it or not, these small creatures can significantly reduce an aircraft's efficiency. In a set of flight tests near Shreveport, Louisiana, the team assessed how well 5 different coatings repel insect residue. Studies have shown that keeping the flow smooth or laminar over a wing can reduce fuel consumption as much as 6%. Even something as small as a bug on a leading edge can cause turbulent wedges that interrupt laminar flow. That results in an increase in drag and fuel consumption. Engineers at NASA developed and tested a number of nonstick coatings in a small wind tunnel back at NASA Langley. Their initial findings allowed them to reduce the number of material from about 20 test samples down to 5. With these 5 best candidates in hand, the team was now ready to place the samples on the right wing of the eco-demonstrator for flight validation. The next step was to find the best bug-infested area in which to flight test the surfaces. After narrowing the list of 90 airports to 6, Shreveport, Louisiana was chosen due to its temperature, geology, runway size, and potential for large numbers of bugs. During 15 planned flights, researchers installed sections of coatings onto the leading edge slats of the eco-demonstrator 757. First, they established a baseline using uncoated surfaces to capture insect accumulation rates. Then, they removed those sections and installed samples of the 5 treated panels. One of the things engineers want to test is how durable the coatings are. Treated surfaces will only be effective as drag reducers if they can withstand the harsh flying environment.
So what we're doing here is testing some of the coatings that we developed to prevent bugs from sticking to aircraft wings. This has been about a 5-year effort, and we started in the lab knowing that the problem is that if bugs stick to aircraft wings, you affect the laminar flow and therefore fuel efficiency. So we've taken samples, designs of material coatings from the lab to wind tunnel tests, and we finally have the big test, which is testing it on an actual aircraft, and so that's what we are here to do. What we do is we mount our samples onto the wing of one side of the aircraft, and we design the test so that half of the panels are untreated that are mounted, and half of them have the surfaces that we are flying. And so what we do is have several takeoffs and landings, because those are the parts of the flight profile where you actually accumulate bugs. And so what we want to do is test to see if the coatings that we developed actually reduce the number of bug strikes that you get, and that's why we fly together with the untreated coatings. And the reason we're interested in that is because an aircraft is designed for cruise. But in order to get to cruise, you gotta pass by takeoff and landing, which is when the bugs are gonna accumulate. And so you basically negate the effect of designing the aircraft to benefit from being in cruise, because you already have the bugs by the time you get to cruise. That's why we have to do a lot of takeoffs and landings, because those are the parts of the flight where we actually have the problem. What we hope to accomplish is that the flight test confirms what we actually saw in the lab, right? So we tested over 200 different compositions in the lab, in a small-scale bug gun, in the wind tunnel, and actually even in a small aircraft. We've down-selected to 5 compositions. If any one of those, or at least one of those, actually works in practical application on the aircraft, which means that we've significantly reduced the number of bugs sticking to the surface, and where they stick is not a critical location to trip the flow, then it would be a success, right? This is actually a long-standing problem. We've seen literature all the way back to the 50s trying to solve this problem. And so if we're able to have a solution based on current understanding of what makes things stick and not stick, that'd be a huge success.
Testing also continues on this unique application, and early results have shown that the ideas that have been generated may possibly work to reduce bug strikes on future aircraft. These are just a few of the innovative ideas that came out of NASA's Environmentally Responsible Aviation project. Only time will tell how many new technologies and innovations will come from the hard work done by this team from NASA. They can be proud that their hard work and efforts will lead to radical changes in aircraft design and efficiency for them and future generations. The results from this team and from NASA in general prove that when we as a country set a goal, if we put the right people on the task and let them work to completion, we can accomplish anything.
Ever wonder what life is like in space? Or what's happening with the science aboard the International Space Station? Well, check out Station Life, daily on NASA TV. It's all about matters of the heart. Hi, I'm NASA astronaut Tracy Dyson, Welcome to Station Life. The focus of today's show is on matters of the heart as they relate to good cardiovascular health. We'll take a look at how NASA keeps astronauts' hearts healthy off the Earth. And we'll take a look at some of the research being done aboard the International Space Station that can keep all of us healthier here on the Earth.
Houston 2 for velocity calculation. Go ahead, we get steps 4, 5, and 4, 6. We're moving on to step 5.
You want to go right now for that activity?
Thank you.
Okay, Tracy, we copy, and that's good information. We'll pass it along.
Cardiovascular disease, including heart disease, stroke, and high blood pressure, is the #1 killer of men and women across America. Fortunately, many studies have shown that healthy habits, including good nutrition and exercise, are important for maintaining a healthy heart here on Earth. Those habits are even more important for astronauts on the International Space Station. Living in microgravity for 6 months changes our bodies in a number of ways. Without gravity, we lose bone mineral density, our muscles atrophy, and our cardiovascular system gets weaker. Some of our studies have shown that in space, the size and shape of our hearts may actually change, which could make it difficult to do our jobs when we get back to Earth or even land on Mars. On Earth, our heart and blood vessels are well adapted to work against the downward pull of gravity. In space, however, there's a tendency for blood and other bodily fluids to accumulate in the upper body. Let's take a look at one of the consequences of this fluid shift.
We have recently identified that some astronauts experience changes in their vision, which might be related to the cardiovascular system. Our hearts pump blood around our body through blood vessels. Special adaptations in our bodies ensure that fluid is evenly distributed with the pull of gravity. In space, astronauts no longer experience the downward pull of gravity, and the fluid in their bodies tends to move towards the upper body and the head. Our cranium is a rigid container. As the fluid moves towards the head, it causes the pressure inside the skull to rise. This is known as increased intracranial pressure. The optic nerve travels from the brain to the eye. The increased pressure from the cranium travels down the nerve and affects the eye. It causes the optic nerve to be squeezed, and the optic disc, where the optic nerve meets the eye, to swell. The back of the eyeball flattens as pressure builds behind it, and the blood vessels in the back of the eyeball also swell. These changes can affect the astronaut's vision. One change is that the astronauts become farsighted. A second change is that they can develop cotton wool spots, which represent damage of the nerve fibers in the back of the eye. These can cause discrete areas of vision loss. NASA is working to understand and prevent these changes in astronauts, which may also help us understand and prevent related vision changes here on Earth.
One of the tools we have to study heart health aboard the space station is an ultrasound device, which uses harmless sound waves to take images of the inside of our bodies. Those images can be viewed at the same time by researchers and doctors in mission control. With minimal training on the ultrasound, remote guidance techniques developed by NASA enabled astronauts to take detailed images of their own heart. In our next segment, we'll travel to a small community in Brazil that has benefited from remote medicine techniques that were advanced by the research aboard the International Space Station.
Minas Gerais é estado.
Minas Gerais is a large state. Our territory is about the size of France, and we consist of 853 units and municipalities. There are large distances between our communities and many very isolated rural communities.
Nós estamos utilizando nova tecnologia.
We are using new technology that impacts the quality of prenatal care and the diagnostic capacity of the primary care doctor in these situations involving distant, isolated communities.
Providing medical care for people in remote locations, like distant rural communities or the International Space Station, can be difficult, because trained medical personnel are not always available. NASA research teams develop techniques that enable astronauts aboard the space station with minimal training to operate an ultrasound device using simple printed guides. The ultrasound images are transmitted in real time to a doctor back on Earth, who can make medical decisions without actually being aboard the station. These same techniques have been adapted for use with portable ultrasound devices in communities where expert medical care is not always available.
We are also incorporating the first aid and emergency care components, improving first aid at the scene of the accident and enabling the use of ultrasound to communicate to the medical communication center. In the ambulance, we can use ultrasound in various situations. In those situations where time really matters, in which you have little time to make decisions. The idea of using ultrasound for healthcare is like an extension of the physical examination. You are able to conduct the exam with much more detail. And you can use it at a time to make a decision, or you can use telemedicine platforms to obtain a second opinion from someone at a distance. My name is Joaquim Diniz. I'm a doctor in the town of Manga. In Manga, people live with a particularity, and that is isolation. We have a geographical barrier that is the São Francisco River, which is both a blessing for the region, but it also isolates us. We live in a region where financial resources are few. People do not have a lot of work, but they are honest, good people who do not have much opportunity. So there are many needy people who need these resources and rely only on this institution to provide assistance. This is a technology that helps us solve many problems. That was the case of a patient who came to the hospital with severe respiratory failure, and the people realized she would die in just 20 to 30 minutes. We talked with Dr. Parzelli, who was training us to use the ultrasound. He came and applied the ultrasound and discovered large amounts of fluid around her lungs and heart. We performed the procedure and drained a lot of fluids. In 10 minutes, the woman immediately experienced an improvement, and in half an hour was already walking. It was like a miracle, a rise and walk. She was dying in front of us without people knowing what was happening. This ultrasound was instrumental in saving the life of that patient.
All right, ladies and gentlemen, boys and girls, space geeks from all over the world, we have with us today a real treat. Dr. Koichi Wakata from the Japanese Space Agency and absolutely one of my favorite astronauts. Actually, in fact, wait a minute. I have a list right here, and I want to prove it. Look, Koichi.
Oh, great note.
TC's top 10 heroes of space travel. Look.
Wow!
He's on there. Welcome, Koichi.
Good to see you, Tracy, here.
Nice to see you, too. Thank you for joining us on Station Life.
My pleasure. I'm always watching your program.
Really?
Glad to be here.
Oh, wow. Did you hear that? I'm so excited that I'm actually honored that you watch our show. It's all about the space station, you know.
Yes. Yes, this is wonderful to be able to explain how wonderful it is to work and live on board the space station.
Yes.
And then today, what are we talking about?
Today we're talking about cardiovascular health.
Awesome.
Yes. And you know a thing or two about that?
Yes, we do exercise pretty much every day.
I was going to ask you on board, did you work out every single day?
I did, because it's not only, to keep, my body healthy, but also it's a very important psychological, I think, relaxation for me. And then the best part of the exercise is the, what is that? The ARED device that we have on board.
Yeah.
It's just sitting right next to the cupola windows.
Yes.
It's probably the best view gym in the entire world, I think.
Absolutely.
Yeah, you can do the muscle strengthening exercise, and at the same time you can see this beautiful home planet. And what a wonderful place.
That's right, because we have the cupola and we have that big center window. We call it Window 7, and then most days, because the space station is oriented with the belly of the space station facing the Earth, which means that the cupola windows are facing the Earth, and there we are on the ARED, above it, below, however you want, whatever your perspective is. But anyways, we're right in line looking out that window, which seems to us like we're on a bench, we're doing our bench press, and we're looking out that window. And I remember doing my exercise one day, and I saw red soil go by, and I'm like, that's Australia!
Exactly.
So yes. you can practice geography at the same time. Can you tell us a little bit about Sprint and what that was all about?
Right, Sprint exercise is a new protocol, and already several astronauts have tried that method. And basically, it uses the prescription of like a higher intensity of exercise, but less volume or less number of exercise days. For example, like if I on board the space station 7 years ago, I pretty much exercised like running for 40 minutes in the same pace. But here, as far as cardiovascular is concerned, we have like a sprint running, like for 30 seconds sprint, and 15 seconds rest, another 30 seconds of run. But it's only like 6 or 7 minutes, very short interval, but high intensity training. And you do that like 3 times a week instead of 7 days a week.
Wow.
And so it's like a smaller number of days of exercise, but the higher intensity. And that's part of the sprint protocol. So 7 years ago when I was on board the space station, I used the previous protocol, which I exercise every day. But this time, it's a smaller amount of time actually. But the results were pretty good. I was able to walk right after landing, and so I think this new protocol is working very well.
Wow, so if you compared when you were on board and landed 7 years ago to now, when you did this new protocol and you exercised more and you had probably more emphasis on the exercise because you have more equipment to work with. A big difference, did you notice?
As for after landing, I don't see very much difference. So that means that's such a very efficient way to do exercise, because if the results are the same, if you spend less time in exercise, that means it's a very efficient way of exercising. So maybe we can utilize that in the future when we go to beyond low Earth orbit, when we go to Mars, and then so a lot of new protocols are being tested on board the station.
Yeah, and I can see where folks back here at home who don't have time to exercise pay attention to this, because you can spend less time working out and get the same benefits as if you were working out for 2 hours or something.
Right.
And you have done just a tremendous amount of work, Koichi, not just in your most recent increment, but throughout your career in the space program, and you've been an asset to Japan and to NASA and to the International Space Station and to Station Life. So thank you so much for being here with us, spending so much time sharing your stories. We've just had a lot of fun with you. So wish you all the best as we go forward. I'll see you, probably in 5 minutes, but, thank you so much for being here with us.
I enjoyed it. Thank you, Tracy.
Likewise.
Glad to be here.
Cool.
Just curious.
I think they can actually put ice in here.
Yeah, depending on how much water pressure we have that day, we can do 16 to any now, and pretty much any time. If we have good water pressure, we can get you up to around 80. But you're saying Tracy's taking off on time.
No, you're the one that was waiting.
Thank you for that. Thank
So with all this exercise going on, is it really working? Researchers and ACERs, who are astronaut strength conditioning and rehabilitation specialists, have made great progress. Before we had a full gym on the space station, our astronauts needed quite a bit of recovery time back here on Earth. Today, our astronauts are coming home in excellent health.
My name is Mark Williams. I'm the lead astronaut strength and conditioning coach. On board at the International Space Station, we have 3 pieces of hardware. We have a cycle, which we call CVIS. We have a treadmill, which is called T2, and we have a resistive exercise device, which is called ARED. And each device is specifically designed to do certain things for the astronaut. We try to do one of those particular devices every other day. One of them we're going to get a little bit better cardiovascular fitness out of it. The other one we get a little bit more impact loading, like running on the ground. So that affects muscle, it'll affect a little bit of bone, does things. Those are the physiological aspects of it. But then also making sure when they come home from a 6-month flight that they don't come home like a bowl of Jell-O. You know, they're going to lose muscle, they're going to lose strength, they're going to lose bone, they're going to lose cardiovascular fitness. But at the same time, then we have to take them, get them back to where they were before they left, which is what we do in our post-flight period once they come home for about 6 to 8 weeks, and just get them prepared back to normal life, you know, doing their job, doing with their family, doing yard work, whatever that happens to be.
Have you ever been sedentary for a long period of time, like lying in bed for a week because of an illness or surgery, and then stood up quickly? Did you feel like you might fall or that not all your senses were functioning? Hi, I'm Dr. John Charles with NASA's Human Research Program. During the 1-year International Space Station mission, NASA will conduct functional studies to gain insight into key physiological factors that contribute to changes in performance. Just like it would take minutes, hours, or even days for your body to acclimate to standing after lying in bed for weeks, it takes time for an astronaut's body to acclimate to an environment with gravity after working without it for many months. 2 tests will focus on post-flight tasks and procedures that will be vital for an exploration crew that has just landed on a planet after a prolonged period of weightlessness. The functional studies will assess how the neurosensory networks, eye-hand coordination, fluid distribution, cardiovascular, and skeletal muscle performance all work together to accomplish an integrated task or function. Researchers hope to compile a post-flight recovery timeline and develop and validate tests to define acceptable performance and define the linkage between physiological changes and functional capacity. This information will be helpful for astronauts and researchers as they prepare for future long-duration missions to asteroids, Mars, and beyond. To learn more about NASA's Human Research Program, visit www.nasa.gov.
So now let's hear from one of our researchers who is studying the cardiovascular system off the Earth for the Earth.
My name is Stuart Lee. I'm the lead research scientist in the Cardiovascular and Vision Laboratory at Johnson Space Center. So the astronauts in space flight is somewhat analogous to if you took one of us on the ground and told us not to exercise for a long period of time. So spaceflight has allowed us to see the deconditioning effects, and we can see all the negative things that can happen when you don't exercise, when you don't do physical work every day that we're actually genetically designed to do. So I would say that cardiovascular health is important from the aspect of the heart and the blood vessels are the communication system in your body. So the experiment that they're demonstrating in the background is the primary measurements in our cardiovascular experiment called CardioWalks. And it's primarily looking at the health and function of the arteries in your body. In this particular case, they're scanning the brachial artery, and we use that as a surrogate for the arteries in your heart, the coronary arteries. So we're able to see how they would respond to stress. And obviously, if they respond well, then we've got good cardiovascular health, and it has a good prognosis long-term for the health of the heart. So they're looking specifically at how the vessel expands and contracts with each heartbeat, and then we stress the vessel, and we see how well it expands. And those are key functions in your ability to adapt to stress when you're exercising or when you're experiencing orthostatic or gravitational stress. And so it gives us a way that we can look at throughout the mission and after the mission how the crew members are responding to the spaceflight experience. So Cardio-Ox is looking primarily at the health and fitness, as you might say, of the arteries. The unique part of Cardio-Ox is we're actually looking at 5 years after the mission. So most experiments just look pre, some in and post-flight. We're actually interested in long-term health of the crew members. 5 years later, were there stresses involved with spaceflight which might have caused some issues for them. Sprint is another experiment that looks at cardiovascular, but it looks primarily at the cardiovascular fitness end of things, how hard you can work. We call it VO2 max or maximal oxygen consumption. How hard you can get your body to work during space. And the VO2 max test is very good because it's an integrative test of the cardiovascular system. It brings together all the function of the cardiovascular system so you can work as hard as possible. So these experiments together give us an idea of what's happening on the functional side of things, the Sprint study, and then on the I don't want to say pathological, but on the health side of things with Cardio-Ox. And then with the Cardio-Ox twins experiment, we're also then looking at how genetics affects those things. My name is Stuart Lee. I'm a lead research scientist in the Cardiovascular and Vision Laboratory at Johnson Space Center. We're working off the Earth for the Earth.
Our International Space Station provides an unprecedented research platform in space, allowing doctors and scientists to conduct science experiments that can't be done anywhere else. For NASA, keeping our astronauts' heart healthy is vital for continuing the journey off the Earth. Here on the Earth, the keys to good heart health are good nutrition and vigorous exercise. Thanks for joining us on Station Life at our behind-the-scenes look at cardiovascular research being done aboard the International Space Station. And as always, be sure to follow us on Facebook and Twitter for the latest research news, and download our app, which is legit, on your mobile device. Until next time, we're working off the Earth for the Earth.
Ever think you might want to be a scientist? Or that you could work with NASA? Well, thanks to citizen science programs, you can. Find out how next on Real World. When you picture a scientist, what comes to mind? A person in a white coat? Someone stuck in a lab? Actually, scientists are pretty interesting people doing some really amazing work. And while some scientists do work in a lab, others work in the field, under the water, or on the computer, the one thing scientists all have in common is that they're looking for answers to some serious real-world problems. But sometimes they need help, so they turn to citizen scientists to assist with their research. So what is a citizen scientist?
I think people are aware that NASA has many different missions. We have missions to Mars, we have missions to Saturn, we have many different missions that are observing Earth. There's all this data coming in. And quite honestly, scientists don't have time to go through it all themselves. And we need people to look at this data to tell us what discoveries might be waiting there for us. So this is a way for the general public to do serious, publishable science with us, results that we need.
One of the longest running citizen science programs is GLOBE, or the Global Learning and Observations to Benefit the Environment program. GLOBE students from around the world conduct research to measure and monitor changes in their environment. These citizen scientists learn to use specific tools before they go out in the field or begin their work on a computer. And they follow a protocol, which is a special set of steps to do their research. Think of a protocol just like following a recipe for a cake. But why are protocols so important?
The most powerful thing about science is that it is a tool to actually discover things about reality. But we all need to make the same measurements in the same way. You have to design an experiment so that anybody, anywhere in the world, could do it the same way and get similar results. There's a thing called a scientific protocol, and this means that wherever you are, we're using the same tools with the same precision, and that means we can all compare our results. For example, let's say that somebody asked you to measure the temperature of where you are. Are you measuring in Celsius or Fahrenheit? What time of day did you take the measurements? Did you do it at nighttime or during the daytime? If we simply ask people what temperature is it, we get all kinds of numbers that don't make sense. But if we specify it needs to be this accurate, you need to use these units, you need to measure this time of day, then all of a sudden we can bring all of this information together and compare it and find trends and make real discoveries about what the world is doing. That's the power of the precision of the tools of science. And that's what a scientific protocol really means.
Citizen science projects may also require you to practice some of your math skills. NASA School, for example, may ask you to estimate the percentage of cloud cover in the sky. Another project might ask for the percent of a leaf that has been damaged by ozone. When the same scientific protocols or steps are used to collect data, that data can be analyzed by scientists to help them better understand the problem they're trying to solve. So what are some other opportunities for citizen scientists to collaborate with NASA?
So which citizen science project should you choose? Well, this is your chance to do a little shopping and let your own curiosity be the guide. The wonderful thing about citizen science is you don't need any special skills to get involved. You, as you stand right now, are prepared to do these projects with us. To me, you really need some curiosity. Are you curious about the planets or about the Earth or the universe? And if you can give us some precision, do the measurements as carefully as you possibly can, that will give us the best results. But you need no special training. Start it tomorrow.
It's pretty easy to get started. Just go to the NASA Citizen Science website, pick a program that catches your interest, then be sure to make careful observations and follow the protocol exactly. Get out there and help. You really can make a difference. See you next time on Real World.
Ever wonder what life is like in space? Or what's happening with the science aboard the International Space Station? Well, check out Station Life, daily on NASA TV.
And we are now under 5 minutes away from the opening of that release window. SpaceX Dragon, the CRS-11 commercial resupply mission, the 11th for SpaceX, getting ready to depart the International Space Station.
Station Houston on 2 for Dragon.
Go ahead on 2 for Dragon.
Okay, Peggy, we are looking good down here. You have a go for Dragon release on time.
With that 1:40 a.m. Central, the release window is now open. So with the window open, we'll stand by for the issuance of the command to release Dragon from Canadarm2. And once the command's given, it takes a little while for the snares to retract and Dragon to be released, and then it'll slowly drift away. Getting the confirmation the snare's open. And as you can see, slowly moving away, Dragon released. And so the robotic arm now being backed away by the crew on board, and the release coming on time at 1:41 a.m. Central, while the station was a little over 258 statute miles over the central part of Australia. So they're now going to back the arm away, and then a series of 3 burns will be executed using thrusters on Dragon to begin taking it away from the International Space Station. Getting a good view right down the barrel of the robotic arm. You can see it continuing to back away. And the visiting vehicle officer confirming the second departure burn has begun.
Copy. Go for step 5 in 1.320 and monitoring step 3 in 1.602.
Good words, Peggy.
Just crossing the Terminator line, that line between night and day on the Earth's surface. Dragon continuing to depart the area from the International Space Station. But everything going smoothly with this morning's operation. We'll just watch for a few more minutes while Dragon heads off into the black. Everything going very well with the end of this SpaceX's 11th commercial resupply mission.
Station, this is Houston. Are you ready for the event? Yes, we're ready for the event. Mr. Brooks, please call station for a voice check.
And that's your cue.
Station, this is Garth Brooks. How do you hear me?
There we go. Can you hear us?
Yes, I can hear you. You sound and look great.
That's fantastic. We decided we would hang off the side of the wall because you can't do too many interviews on Earth when you're, hanging on a wall.
Do you guys get used to just that position, or is there any time where the gravity's at your feet at all? Is there a room in there, or do you have to wait to get back? That's unbelievable.
Nah, we have to wait till we get back, but it's really not a wait. We kind of like it up here. Being upside down or sideways is pretty fun. And hey, I just wanted to say something to you, sir. One of my heroes is William Shakespeare. He puts, he just made every word count and every phrase and And the line and passage that he had so much depth and meaning. But when it comes down to it, sometimes it's the actor that brings those words alive. And I think that you have so many great songs and so many great messages, but it's the heart that you put into every performance and the soul that you put into all those songs that make them so impactful. And I know for me, The River in particular was pretty much my anthem for the last almost 3 decades. So thank you from the bottom of my heart for being such an inspiration to so many and making those words count. Thank you, sir.
Wow, thank you. That's very sweet. Thanks for hearing the music. That's the cool part of it. And thanks for letting me get to be a part of it. Somebody said The River might be a song that you're familiar with.
Yes, sir. That was the first song they played for me on the launch pad. So it's a lot of meaning.
Can I ask you why?
Well, because of what it represents. The dream is like a river. It does change as it flows, and you know, with the good Lord as your captor, it can. I could go through every word of the song, but I do a better job of it. Every single word has meaning, and it's true. Dreams are changing, and you know, people ask us about being astronauts and what's that dream like, and you have to find something that you're passionate about and that you love, and then you follow it and you see where it goes, and the good Lord's going to put you where you should be. And that's what that song says, and that's why it means so much to me.
That's sweet. Dead on. I noticed we've been watching you guys for a while. I noticed the gentleman from Russia pop back there. And what's it like up there where there's nothing other than what you have in common is why you're together? That's got to be a great feeling. And I bet you guys probably just forget that you're from different places at some point.
Well, I do think that up here on orbit we have kind of an international culture. It's one where we're supportive of each other as a team and not worrying about what nationality we are. I think that's important.
Yeah, and I would think the nationality just be defined on your knowledge of stuff and sharing that with each other. That's a great message for all of us down here to follow. Miss Peggy, you're a rock star.
No, I'm not.
Yes, you are. Your credentials list a mile long. Congratulations. I just love you guys to death. This is very sweet. Thank you for this. I know we don't have much time, so we have some gifts, if you don't mind, that we would like to share with you, especially you, Two Fish.
Well, that sounds great.
I want to introduce you to my better 99.9%. Miss Sherwood actually made the trip with us here today, so I wanted to come talk to you.
Hi.
Well, how you doing? How's that for a power couple?
I've just been watching you guys and listening to both of you, and just thank you both for your service. I know Garth has probably said all that, but just honored to be here, and I can't get over it. I'm enjoying the spinning microphone and the socks. You guys, the socks are on point.
Yeah, yes.
Hey, it's the 4th of July coming up. We got to start representing early. Wait till you see what we're wearing on the 4th.
I can't wait. Is it okay for me to give them a gift?
Please.
Okay, I have a gift for you two fish, actually. Actually, I have 2 gifts for you that are here. Elizabeth and Soraya are here to say hi. You know, your wife and daughter, you remember them, right?
Oh, yeah. That's the best gift.
Good morning. But I'm not going to talk. I'm going to let you talk to the megastars.
Hey, Daddy.
They're so squirt. I love those words.
Good morning, kiddo. Good morning, hottie pants.
So cool. She wants you to talk.
Okay.
She's going to want to talk to you.
Thank you very much. 2 seconds, I'll be right back. Okay, it's all you.
So my question, of course, is about the food. How are you liking the food up there, and what do you recommend?
I think my favorites would be chicken fajitas. Brownies aren't bad when they're warmed up, and mac and cheese is always a winner.
That's a good one.
So there's quite a few that are actually pretty good. It's just, you know, they get a little old after a while.
Chili pepper.
Kind of like at home.
And as Jack's point, yeah, somewhat sometimes. But as Jack points out, we say up here it's all about the sauce, because it's kind of like, what are you going to have with your chili pepper paste or your sriracha sauce or other kinds of sauces.
And you can just basically dip in the sauce as it's flying by, so you're in good shape there. That's pretty good.
Why don't you ask them what their favorite thing is, and you'll make it when they come back down.
Well, that's a good.
Actually, usually we squirt it on something and then use it as glue to hold it to the tortilla.
Garth has a good suggestion. He says you guys let us know what your favorite stuff is, and when you get back home, I'll make it for you.
Okay, it might not involve anything we're eating up here, but Jack wanted to do a demonstration for you. He wants to show you how fluids are different in space. And this one is tropical punch. And you can see that surface tension plays a much, much bigger role up here. So it just forms a sphere. So all our drinks, we don't drink anything out of a cup because you wouldn't be able to hold it there, but they form balls. And so we have straws with special clips on them to hold it closed when we're not drinking out of it. So it's a very different experience from that perspective. But it's actually why the science actually works well up here. Without gravity, a lot of the things that affect, for instance, protein crystallization or other types of crystallization involves gravity. And so our science up here is great.
That makes all kinds of sense. Yeah. So again, man, thank you very much for letting the music be part of your life. Thank you for what you said. If you don't mind, because I've never got to do this, I would love to, let me play you a little something over here. And I don't know how this is going to work, but we're going to find out.
Okay, here, let me get away from Brian.
Oh my God. I'm pretty sure that's a rule of spaceflight. Never turn Garth Brooks down when he wants to play something for you.
Of course.
Yep.
No, a dream is like a river, ever changing as it flows, and the dreamer's just a vessel that must follow where it goes, trying to learn from what's behind you, and never knowing what's in store makes each day a constant battle just to stay between the shores. And I will sail my vessel till the river runs dry, like a bird upon the wind. These waters are my sky, I'll never reach my destination if I never try. I will sail my vessel till the river runs dry.
Dude, awesome. I got goosebumps everywhere. Woohoo!
We love you guys. Love to your families. God protect you and keep you, get you back home safe. Okay, thank you for everything, and tell your buddies there in the place we love them as well. Okay.
You got it. Thanks so much. Thanks for coming, and I hope you have a great tour there at NASA, see some of the great stuff we have to offer. If you ever want to come back and be part of our training or whatever, just let us know, and we'll say the word, and we'll have you.
That's a deal, man. Thank you very much. Again, safe travels.
Thank you, guys. God bless you.
As you leave, you can see the Space Ninja spin.
Take a selfie.
Do they know?
Station, this is Houston ACR. That concludes the event.
And Station, thank you very much. They're taking a selfie here in Mission Control, if you're able to pose for a quick photo.
Absolutely.
Exactly. So that whole trip is in the daylight is
Exactly.
45 minutes?
Yes.
My goodness.
Takes 90 minutes to go around.
16 sunrises and sunsets. Oh, so you're lapping every 90 minutes?
Yes.
And,
15 minutes. So we have Japanese model, European model, US model.
So you've never
What's the oldest
No,
model?
even all the times I've been here, there's been, I had one opportunity to come here on another visit and I couldn't come.
It was on the robotic arm, and we let it go, had springs, and it
Is it tomorrow?
went to Earth.
Yeah.
And
When does it come
We
back?
were there last weekend.
it'll burn up.
And you still got your parents?
Oh, yeah.
How they do it? You look directly into the sun on that thing?
You can.
And what
it
does it do?
pretty
It
much
just washes everything out?
But you do get a lot of lens flare with these because we see.
So,
We
do you
are-
guys sing to these people over the phone all the time?
No.
Nobody, huh?
It's very, very rare.
Only if we want to punish them. Because of that, John F. Kennedy Space Center in Florida, Lyndon Baines Johnson, the vice president in Houston, and then there's 8 other NASA field centers, including headquarters in DC. And so this is human space flight right here. All human space flight is performed at the Johnson Space Center. And so it's
When was this? When did you move out of this to maybe?
1996. We started in the early 90s, and we said, you know, this got us to the moon. We flew 76 shuttle missions out of this. In fact, the room you were in before looked identical to it. I give a quiz.
Like who knows? Like who knows it? Who's what it
It's
is?
shocking. And what,
You ready?
Yeah.
Tell when you're ready.
But it looks like a disaster's happening.
Wait.
That's great.
Minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 2, 0.
Second stage ignition.
anticipating roll rate spikes at deployment.
A doors.
Now seeing the doors coming off, and you'll see the ampoule injection
MB doors
from the payload. And you're now seeing the payload as it's reached apogee and is starting to descend back down towards the Earth. The bright light that you see, of course, is the sun from that altitude.
We just have a few minutes here, and we were going to be starting this contact. I want to give you, the first thing I was asked to do is to ask everybody to take 3 steps back and to be an engineer or a mathematician. And so the wireless technologies we're going to use today, which are all shown here, everybody's ready? Over there are the antennas.
This is A1SS on Channel 5. How do you hear?
I hear you fine, Jack.
Thank you very much. And
this is Zoe. What has amazed you the most about being in space? Over.
Zoe, I think it's... Well, I guess you could if you had enough time. I know that we take pictures of glaciers and different ecological targets.
And we are now under 5 minutes away from the opening of that release window. SpaceX Dragon, the CRS-11 commercial resupply mission, the 11th for SpaceX, getting ready to depart the International Space Station.
Station Houston on 2 for Dragon.
Go ahead on 2 for Dragon.
Okay, Peggy, we are looking good down here. You have a go for Dragon release on time.
With that 1:40 a.m. Central, the release window is now open. So with the window open, we'll stand by for the issuance of the command to release Dragon from Canada Arm 2. And once the command's given, it takes a little while for the snares to retract and Dragon to be released, and then it'll slowly drift away. Getting the confirmation the snare's open. And as you can see, slowly moving away, Dragon released. And so the robotic arm now being backed away by the crew on board, and the release coming on time at 1:41 a.m. Central, while the station was a little over 258 statute miles over the central part of Australia. So they're now going to back the arm away, and then a series of 3 burns will be executed using